Today's notes will cover radical simplifying and also squaring of radicals and binomials. You'll need IC46 for our work today if you want to track that down to be able to follow along. The first focus, one, is going to be simplifying radicals. This is going to be important for problems where you're asked to give your answer in what we call exact simplified form. In order to get to exact simplified form for radicals, you have to show your work. Work must be shown. For some of our scales, if we can't see the work for the radicals, the max score you can get is a 2.5. So you want to make sure that you're choosing one of these three ways to demonstrate your work. So we're going to go through the three examples that are already pre-printed on the page so that you can understand what's happening, and then I'll show you how those actually look with a few examples. All right. So the first method that you are able to use is to focus on the largest perfect square. So perfect squares are numbers like 2 times 2, 3 times 3, 4 times 4, 5 times 5. If you don't have your perfect squares memorized, this method might be a little bit tricky for you. But basically, you're going to consider every perfect square until you get to one that's larger than the number underneath the radical. The next perfect square is 100, so I know that I'm done with my list. And then the goal is to determine the largest number out of that list that you can divide 96 by. So if you're not really good at mental arithmetic, you can use a calculator and you just test. 96 divided by 81, no good because we got a decimal. Divided by 64, no good, we got a decimal. So you just keep going until you find the largest perfect square that you can divide 96 by. In this case, it's going to be 16. So we rewrite 96 as a product, as a multiplication problem. When you do your division and you recognize that 16 works, it tells you what the rest of that product is. So it's going to be 16 times 6. The square root of 16 is 4 because it's a perfect square. The square root of 6 is not an exact value, so we leave it as root 6. For root 6 is the exact simplified form of root 96. So that's one option. Remember, you're testing your perfect squares from largest to smallest until you find the biggest one that works. Option number 2 might be familiar to you from middle school when you're dealing with radicals the first time around in like a pre-algebra class. We can split this value any way we want. So we could use the same values that we used over here, 6 and 16, but this could also be any other two numbers that multiply to be 96. Those are called factors. So we could have noticed that 96 was even and just divided it by 2, and then these would have been 2 and 48. If one of the numbers can be broken down into more factors, we keep going. So 6 is really 3 times 2. 16 is really 4 times 4, and then if you want to, you can keep going, but we also could have stopped here because our goal is to make it to a point where we notice pairs of factors. So if we make it all the way to what we call the prime factorization, we have 2 pairs of 2's, and then we have a 3 and a 2 that don't have a matching pair. We're just considering the numbers that are at the ends of the branches. So each pair of 2 results in a 2 out front of the radical, and anything that doesn't have a pair goes back to the inside of the radical, using multiplication in both cases. If we had not filled in the bottom of this and had just stopped here, then this pair of 4's would have resulted in a 4 out front, which is exactly what we get when we put those two 2's back together, and then we would have had the 3 and the 2 that combine back together to be 4 root 6. So we get the same exact simplified form. It's always going to be 4 root 6. It's just a matter of how you're showing the work to get there. So if you're going to use the largest perfect square method, this is what your work looks like. You show the largest perfect square and the leftover factor, and then you simplify. If you're going to use a factor tree, this is what your work looks like, and then you show how that results in the exact simplified form. All right, option number 3 is to use what we call a factor table. So root 96, or 96 itself, can be broken up as 1 times 96. We test to see if this has a perfect square. or is a perfect square. The way we can do that is by using our root. So that is not a perfect square because it gives us a decimal. So the next thing we do is we find the next pair of factors. 96 divided by 2 is 48. So 2 and 48. Test this by square rooting it. Gives you a decimal, so that's not a perfect square. 96 divided by 3 is 32. Test 32 to see if it's a perfect square. If you don't know, it's not. 96 times 4 is 24. Test 24 to see if it's a perfect square. It's not. We can't do 96 divided by 5, so we skip it. It would result in a decimal. 96 divided by 6 is 16, and boom, we landed at the biggest perfect square. If that hadn't worked, we would keep looking for other factor pairs, keep checking whether the big number is a perfect square, but if it's not, then we wrap back around and we look for a perfect square on the other side. Since that's a perfect square, we square root that to get the 4, and the other part of that factor pair goes back to be inside that radical. So again, 4 root 6 is the result, but your work looks different. Okay, you're going to choose one of those 3 methods. It does not matter which one you choose, so you just need to kind of feel it out, practice them, see which one you like the best. I'm going to do these problems multiple ways just so that you can see an example that matches what you are thinking about using. All right, root 12 or radical 12. If I'm going to do largest perfect square method, I'm looking through these perfect squares and my only options would be 4 and 9. 12 divided by 9 is a decimal, but 12 divided by 4 works. So I would rewrite this as root 4 times 3. Root 4 is 2, and then the 3 stays inside. So that would be method number 1. If we were doing method number 2, we would take that 12 and we would split it into 2 factors. I'm going to choose 2 times 6 because that's the first thing I think of. 2 can't be broken down any farther into factors, but 6 can be split as a 2 and a 3. They're now all prime numbers, and I notice a pair of matching 2's. So that pair of 2's becomes a 2 out front, and this leftover 3 goes back inside the radical. 2 root 3, but method number 2. All right, last option is that factor table method. So I'm thinking about 12. 1 times 12, 12 is not a perfect square. 2 times 6, 6 is not a perfect square. 3 times 4, 4 is a perfect square. The square root of 4 is 2, and the leftover factor is 3 to be inside that radical. Method number 3. So again, it doesn't matter. You don't need to do the problem 3 ways, but I'm going to do the examples multiple ways so that you can try to make a good choice about which method you like the best and want to practice. All right, next up, square root of 40. So if I go through my perfect square list, I would start at 36. 40 divided by 36 is a decimal. Same thing with 25. Same thing with 16. Same thing with 9. So 4, again, is the largest perfect square. I'm going to write that out to the side this time to save myself some space. It'd be 4 times 10. The square root of 4 is 2, and then the 10 would stay in the root. Again, that would be option number 1. For option number 2, I would do a factor tree. So I might split up 40 as 5 times 8. Maybe that's what I think of first when I think about things that multiply to be 40. Maybe you thought of 4 and 10 or 2 and 20. Lots of options. 5 is prime, so that part's done, but 8 could be 4 times 2, and then 4 could be 2 times 2. I'm going to look at all the numbers at the ends of the branches. I see a set of matching 2's and a leftover 5 and 2. So a 2 from that pair goes out to the front. The 5 and the 2 multiply back together on the inside to give us the same 2 root 10 answer, but that's method number 2 using a factor tree. Last option, I know this gets a little crowded in here, maybe I'll use a different color to help it make a little bit more sense. Last option is to think about a factor table. So we would list 1 and 40, but that doesn't have a square root because it's not a perfect square, or doesn't have an integer square root. 2 and 20, the square root of 20 does not give us an integer because that's not a perfect square. 40 is not divisible by 3, so I skip it. 4 times 10, square root of 10 isn't going to work out nicely. 5 times 8. The square root of 8 doesn't work out nicely. 40 can't be divided by 6, and 40 can't be divided by 7, and then I would get to 8, which is already in my table. So there are no perfect squares on this side of the table. So I wrap around and I keep looking on this side of the table until I find the largest one. That's a 4. Square root of 4 is 2, and the factor pair that goes with it is 10. So same 2 root 10 answer, but that's method number 3. Okay, you decide, now that we've seen 2 examples, which one you want to try for root 18 and root 75. I'd like you to pause the video, go try out your preferred method, and then when you come back, I'll have something for you to look at so that you can check your work to see if you use that method correctly. I'll see you back here once you do those 2 problems. All right, welcome back. For root 18, if you use method 1, perfect squares, you should have identified 9 times 2, so gotten 3 root 2. If you use method 2 with a factor table, yours might look different than mine because you might not have used 3 and 6 to start with. You could have used 2 and 9. But then when you break it down to that prime factorization, you're going to have a pair of 3's and a leftover 2. So a 3 out front and then root 2. Method 2, factor trees. If you do a factor table, the second entry in your table has the largest perfect square right there, 9. So that root 9 becomes 3, and then that leftover factor goes back into the root. 3 root 2, method number 3, factor table. All right, last example, root 75. If you are a perfect square person, you should have identified 25 as the largest perfect square. That's going to turn into a 5 root 3. If you are a factor tree person, you might have chosen 3 times 25 or 5 times 15. But you're going to end up with a pair of 5s somewhere at the ends of those branches. So a 5 as your coefficient, and then root 3 for that leftover value. And then last but not least, if you're a factor table person, 1 times 75 doesn't give you a perfect square. 2 doesn't work because you would get a decimal. But 3 times 25 identifies that perfect square. That square root is 5, and then the 3 returns to the radical for another way to get to 5 root 3. Okay, feel it out, practice one of those 3 options consistently. Any of them are fine, but you have to have the work to go with whichever one you pick. All right, part 2 of IC46 is focusing on squaring expressions. So when we square an expression, we are talking about having an exponent equal to 2. That means that the expression is going to be multiplied by itself. That's what squaring means. And so if we're specifically squaring a radical expression, what's going to happen is we're going to get a whole number. Not a radical back, but a whole number. Let's see why that happens. So if I take root 6 and I multiply it by itself, that would look like root 6 times root 6. Since those are both underneath radicals, we can combine it to be the square root of 36. 36 is a perfect square. So if we test or calculate the square root of 36, we get just regular old 6. So what is happening here is a square root and a square are actually inverse operations, kind of like adding 2 and subtracting 2. And so what's left behind when we both square root and square 6 is just 6. Using that idea, if we both square root and square 19, we're just going to end up with 19. If we wrote out the work, it would look like 19 as a root times another one, which would give us a big number. 19 times 19 is 361, which you might not recognize as a perfect square, but if you type this into your calculator, it's going to send back that answer is 19. All right, C and D are a little bit different because there's a coefficient. That coefficient is inside the parentheses though, so that means it's part of the squaring process. What's going to happen is those coefficients get multiplied together to give you 3 squared, and then these roots get multiplied together to give you a larger root Or, if you remember, a root times itself is just going to give you that regular number. So what's really happening here is you're doing 3 squared, 9, root 15 squared, 15, and then those two things are multiplied together to give you your final answer. For this one, 135. All right, same thing here. When we multiply 6 root 30 by itself, 6 times 6 is 36. Root 30 times root 30 is 30. 36 times 30 will be our last calculation. 1080 will be the result. One last squaring task for today. We're squaring binomials here. Binomials are expressions that have two terms connected with addition or subtraction. When we square a binomial, the result is going to be a trinomial, a three-part expression. We're going to go back to that definition of squaring being multiplication by itself. So we're going to write x plus 5 times x plus 5. X times x is x squared. X times 5 is positive 5x. And then positive 5 times x is another positive 5x. Positive 5 times positive 5 is 25. We've got some double distributing happening here, or a past teacher might have called that FOIL, first outside, inside, last. These are like terms in the middle, so we'll collect those two together to give us 10x, and that is where the idea of a trinomial comes from, a three-part expression. Same situation here. 2x plus 1 is squared, so it's multiplied by itself. 2x times 2x is 4x squared. 2x times positive 1 is positive 2x. Positive 1 times positive 2x is another positive 2x. Positive 1 times positive 1 is positive 1. Like terms in the middle with those 2x terms. So 4x squared plus 4x plus 1 is our trinomial answer. Last problem has subtraction, so we're going to be a little bit careful with our multiplying. 3x times 3x is 9x squared. 3x times negative 2 is negative 6x. Negative 2 times 3x is another negative 6x. Negative 2 times negative 2 is positive 4. The like terms this time are both negative. Negative 6x minus 6 more is negative 12x. So our trinomial has a subtraction sign in the middle for that final problem instead of an addition sign. All right, that's it for today. Thanks for watching. We'll see you back in class.